Hello, and welcome back to the course on quantum mechanics. This is now the last lesson for chapter 5. So, before we proceed, let's review what we have discussed in the previous chapters, or the previous lessons. So, we have introduced the concept of quantum spin statistics depending on the distinguishability of the particles in a system. If the particles are distinguishable, then we use classical statistics, but if the particles are identical, we use quantum statistics. And we use Bose-Einstein for bosons and Fermi-Dirac statistics for fermions. So in this last lesson, we will be generalizing the concept that we have presented in the previous lesson, which is on quantum statistical mechanics. So suppose you have an arbitrary potential, energy U, and there are n particles in this potential, where n is just the total number of particles, or the sum of all the occupation numbers, n1, n2, and n3, and so on. And the general configuration is this one, the collection of all occupation numbers, n1, n2, n3, and so on. And you have single particle energies, E1, E2, E3, and so on. And each of these single particle energies, have degeneracies d1, d2, d3, and so on. So it's just the number of states with the same energy. So the lowest value of the degeneracy d is actually 1. So when d is equal to 1, meaning there's only one state in that energy level. So it's non-degenerate. D is equal to 1 means it's non-degenerate. So the question now is, how many states correspond to a particular configuration? So this is actually very hard to manually count, because our n here can be a very large number. So the answer will be a number, q, and it will correspond to a particular configuration, the q for a certain configuration, n1, n2, n3, so on. And the answer to this, the value of q, will depend on whether these n particles are distinguishable or identical fermions or identical bosons. So for the first case, for the case of distinguishable particles, the number of particles for a specific configuration is given by this one. So you have n factorial. Again, n is the total number of particles. And then you have a product. This is not a summation, this is a product. Product over n, and n starts from 1 to infinity. So dn is the degeneracy, n sub n is the occupation number. So this is the number of particles for every configuration for identical fermions. And this is the number of particles for every particular configuration for identical bosons. Okay. So let's have an example. So in our previous problem for the distinguishable case, 3 distinguishable particles trapped in a one-dimensional infinite square potential, we actually have this list of states corresponding to each configuration. Now, let's try to verify the number of states in a particular configuration. Of course, we can just count. So for this configuration, the number of states 1. For this configuration, the number of states is 3. And for the last configuration, the number of states is 6. So let's verify that using the formulas that we have introduced earlier. So this is now the formula for the distinguishable, if you have distinguishable particles. So let's first start with the first configuration, wherein 3 of the states, or 3 of the particles, are in the state psi 11. So from the formula, you have n factorial, so 3 factorial. And we will start with the product. We'll start with n is equal to 1. So you have d1. So assuming 1. Assuming it's non-degenerate. Actually, it doesn't matter. Because you raise it to the power of 0. So Wait. So we don't know the degeneracies of the other states except for the state psi 11, which has a uh, degeneracy of 1. There's only one state in this configuration, and it has an occupation number of occupation number of 3. So this is for the n is equal to 11, and for the other states until the state psi 19, we don't know the degeneracy, but since it's still raised to the power of 0, then you will get 1 over 0 factorial, which is just 1 basically. So basically 1 times 1 times 1, you have all many ones there. So you have 3 factorial over 3 factorial, and you will get 1. Verifying that there's one state in this configuration. Now for the second configuration, 5, 13, 13. So there's one particle in state psi 5, there's 2 particles in state psi 13. And state psi 5, it's 1 to the degeneracy is 1. Sorry, the degeneracy is the number of particles in that specific state. So in this case, the degeneracy is always 1. We'll assume there's only one single particle state for every single particle energy. So that is actually what we have discussed when we discussed about the infinite square potential. This is the energy level or energy for this specific state psi n. So it's non-degenerate. So the degeneracy is 1. Okay, so the degeneracy is always 1, so you can actually put this into 1, but anyway, it's raised to the power of 0, so it's still 1. So you have 1 to the 1 over 1 factorial, and in the state psi 13, you have 1. Occupation number is 2 over 2 factorial, so you will have basically 1/2. So 3 factorial is 3 times 2 times 1. So 2 will cancel and you will get 3. So there are 3 states for this particular configuration. You can also do the same for the third configuration. You will get 3. And for the last configuration, you will get 6. Okay. So general quantum statistical mechanics is actually very ideal for large number of values, large n. It's actually impractical if you apply it to a system like this, but we just do this for verification. Okay, so in the previous lesson we discussed about finding the most probable configuration. It's just very easy because you can just list all the possible states. But if you now have an n number of particles, essentially you will now have a large number of possible energies and large possible number of states. So what you can do to find the most probable configuration is to maximize Q. So if you maximize Q, the answer of that is the configuration n1, n2, n3, and so on, which corresponds to the largest value of Q. That's how you maximize a function, right? If you have f of x, if you maximize f of x, you're actually trying to find the value of x which makes f the largest. So we'll try to find the configuration which makes Q the highest. So that's the most probable configuration, the configuration with the largest or the biggest number of states, Q. Okay, so if you maximize a function Q, the answer to that is just the same as maximizing the function of ln of that Q, where Q is a number. So if you maximize a number, the answer to that is just the same as maximizing the ln of that number. So in this case, we use Lagrange multipliers, alpha, beta, gamma, or lambda 1, lambda 2, lambda 3, lambda 4, and we maximize ln of Q. We use the constraints that the total number of particles, the sum of all occupation numbers, is the n, and that the total energy is just the sum of occupation number times the energy. So this is now our function to be maximized. It's ln of q plus the Lagrange multiplier alpha times the constraint. This is actually basically 0. And the other constraint beta. So we have two constraints, which means we need to use two Lagrange multipliers. So use the first derivative test, which means the derivative of g with respect to our occupation numbers n1, n2, n3 must be 0, and its derivative also with respect to the constraints or Lagrange multipliers alpha and beta must also be equal to 0. So using that, we can actually obtain the most probable occupation numbers, n sub n. So for the distinguishable particles, it's given by this one. For the identical fermions, it's given by this equation. And for the identical bosons, it's given by this equation. So the difference between the identical fermions and bosons is that in the denominator, it's plus 1 for fermions, minus 1 for bosons. So what is the physical meaning or significance of all the Lagrange multipliers that we used, alpha and beta? So beta is actually temperature. It's 1 over kT. Kb is just a Boltzmann constant, so meaning it's basically temperature or inverse of the temperature. And alpha is basically the chemical potential energy, mu, as a function of temperature. So the total energy, if you have a distinguishable case, is just basically for every degree of freedom, you have 1/2 kT. So if you have 3 degrees of freedom, you have 3/2 kT. And if you have n particles, so you have 3/2 n kT, the total energy of an ideal gas. So if we now try to find the most probable number of particles associated with a single particle energy En, we need to divide the most probable configuration number or most probable occupation number with the degeneracy, and we shift. In this case, we shift from En to epsilon for the notation for energy, and alpha to mu, and beta to temperature. And this is now the spin statistics if you have distinguishable particles, Maxwell-Boltzmann statistics, Fermi-Dirac statistics if you have identical fermions, and Bose-Einstein statistics if you have identical bosons. Okay. So if you have distinguishable particles, the total energy again is just 3/2 n kT, and the chemical potential energy as a function of temperature can be solved, and it's equal to this one. If you have identical particles, then the energy is given by this integral, and the total number of particles is given by this integral here. So let's have an example. So find the Fermi energy and total energy of fermions at absolute zero. So you need to use Fermi-Dirac statistics here because we are dealing with fermions. So we need to use this integral for the total number of n. So this is our most probable number of particles associated with the number of particles associated with energy epsilon. So you will notice here that when the temperature, since we are trying to find the energy at absolute zero, so when the temperature approaches zero, you will notice that this exponential here will become, so over zero, E minus mu over zero, it's basically infinity. So it now depends whether it's e to the negative infinity or e to the positive infinity, whether the energy is less than the chemical potential energy at absolute zero, where the chemical potential energy at absolute zero is actually the Fermi energy. So if it's less than mu, if E is less than mu, then it's negative. So you have e to the negative infinity, and e to the negative infinity is 0. So you have 0 plus 1, so 1 over 1 is 1. But if E is greater than mu at absolute zero, or E is greater than the Fermi energy, then this becomes e to the positive infinity. So e to the positive infinity is infinity plus 1 is infinity, 1 over infinity is 0. So the number of particles with energy E when t approaches absolute zero is either 1 or 0. So if we take this integral and solve for the total energy. So we obtain this value where the Fermi energy is just given by this equation. So it's actually this one, V over 10 pi squared mh bar cube. So this is the total energy of the fermions at absolute zero. So at absolute zero, the fermions are either they are the number of fermions for a specific energy is either 1 or 0. It's either occupied with one particle or not. So let's focus, by the way, on Fermi-Dirac statistics. So in the previous problem, we have discussed that as the temperature approaches 0, the value of n is either 1 or 0. So if you plot this equation at different values of t, now when t is equal to 0, it becomes like a step function. So it's either 1 or 0. But as you increase the temperature, the curvature actually, it curves depending on the temperature. So as the temperature increases, it curves. But the average value of n is actually 1/2 or 0.5. That one. So that is one feature of the Fermi-Dirac or Fermi-Dirac statistics. So at absolute zero temperature, so the number of particles for a specific energy, or the number of particles in a certain energy level, is either 1 or 0. It's either occupied or not. So for Bose-Einstein statistics, one application is what we call BEC, or Bose-Einstein Condensation. So this actually happens when you lower the temperature of material, such as a gas or plasma, to a critical value, Tc, such that its chemical potential energy becomes 0. So in that case, below the critical temperature, all of the particles are in the ground state. So below that critical temperature, the particles in your material are in the ground state. So meaning, this material will inhibit or exhibit quantum effects at the macroscopic level. So your material will exhibit quantum effects. And some of this, a consequence of these quantum effects is superfluidity and superconductivity. Superfluidity is you have a superfluid, a fluid that if you stir it, it will never stop. There's no friction in the fluid. There's no fluid resistance. And for superconductivity, there's no electrical resistance. So it's a superconductor. It will conduct all of the current to flow within it with no electrical resistance. So in this case, the number of particles in the ground state is given, again, can be solved using this integral, where the number of particles for the ground state energy is given by this one. So kB over Tc. So mu is equal to 0. The chemical potential energy is 0. And we will obtain the critical temperature to be approximately given by this value. Okay, so that is the end of this chapter. Basically all about quantum statistical mechanics of distinguishable and identical particles. So in the next chapter, we will be discussing about perturbation. So what if your system is now perturbed by an additional potential? So what will happen now to the energy levels and to the states of your system? So I will see you again in the next chapter.